Welcome back to Kitchen Chemistry with Mrs. Engel, and today's topic is molarity, or how do we determine the concentration of a given solution. Now, as you can tell from my two plastic cups here, both of these are solutions. Both of them are solutions of food coloring along with water. But the difference is in what you visually can see is the depth of the color. Probably if you looked at these two, and I'm going to put a piece of white paper behind so you can see even better, you can see that there's a variance in the color of blue. This one is obviously much deeper in color than this one. From the vernacular or our academic vocabulary that we use on a daily basis, we would say, well, this one is more concentrated based on its color, and this one is dilute based on its color. Concentrated would mean that it has a greater quantity of food coloring per quantity of solution, and dilute would have less quantity of food coloring to quantity of solution. And that's great. That's great. If I said to you in the laboratory, be careful today, there's concentrated acid out, you would know, ooh, that's the dangerous stuff she's talking about. It's definitely going to hurt me. But from a chemist's perspective, we want to know specifically, what are we talking about? What do we mean when we say something is concentrated or something else is dilute? And so we quantify it. And there are different ways we quantify in chemistry. We are only going to focus on one. Again, if we were back in the classroom, if we had more time, we would be focusing on a variety of ways that we look at the concentration of a solution. But the most common one, and when I order for our department and I order in anything that is a solution, whether it be hydrogen peroxide, ethyl alcohol, isopropyl alcohol, hydrochloric acid, sodium hydroxide, or even a silver nitrate solution, I am going to order by molarity. So let's talk about that by looking at the board. What is molarity? Molarity tells us the quantity of moles of solute per liter of solution. Now notice that that's not solvent, that's liters of solution. And that's because we're looking at a volume of space. Liters is volume. Volume is the amount of space a substance occupies. But we can't just look at the water, because when I add anything to a solution, let's say I wanted to put more, let's say this was a pure substance now, pretend with me, this is pure blue dye, and I'm going to add it to a solution. Well, when I do that, my volume increases. Anytime, whether it's a solid, a liquid, a gas that you're putting into another substance, it's going to take up bigger space, more volume. So we don't talk about liter of solvent, we talk about the liters of solution. Now, the higher my molarity, the more concentrated it is. So if I'm in the laboratory and I have 0.1 molar HCl, that's what I typically put out to you, for you to use, I would say, hey, that doesn't seem so bad compared to 3 molar, especially if I'm dealing with the same amount of volume. 0.1 molar, 1 liter, would mean I have 0.1 mole of HCl per liter of solution. I have 1 liter here, 3 moles of HCl. Obviously, 3 moles is more concentrated. Now, knowing this, you can see that I could create a variety of problems for you to solve. And I'm going to go through a basic one with you today, and then you can determine, and we will determine together, all the different variations I could do. So let's pretend I'm going to make a salt solution. And my salt solution contains 125 grams of NaCl. Well, right away we know that if I give you 125 grams, but my equation asks for moles, I need to convert. Now, where did I get 58 grams from? Molar mass of NaCl. Going to your periodic table, we've been doing this since before the pandemic closed us down. Na is 23, Cl is 35. Add them together to get your 58. This converts to I put this into a flask and I'm going to now add solvent, typically water, until I reach 500 milliliters. Now again, I'm not just adding 500 milliliters of water. Because the salt takes up space as it dissolves into its ionic particles, I'm going to add water until I reach a total volume of 500 milliliters. But look up here, liters of solution, milliliters. This is one of my favorite tricks that I will often give you milliliters and expect you to convert it to liters. Move your decimal place over 3.5 liters. Now we're ready to do division. Plug and chug, as we like to call it. Put it into your calculator. 2.16 divided by 0.5 is a 4.3 molar solution. Now, oftentimes, a lot of the little containers that you use in the lab is because someone has made those solutions. You can get a job in college. I had this job in college. The professors would tell me the list of solutions. I would go in on a Thursday night after my classes. I would make all their solutions for them. If you work in industry, this is some of the things that you would have to do. If you work for the Shedd Aquarium or the zoo, you would be making solutions. Solutions to clean tanks, solutions to keep a pH at a specific area. So again, it is moles per liter. Now, I can ask you to solve for any of these. You can allow your X to be at molarity, at moles, or liters. All that means is converting. If my X is moles, molarity times liters will equal moles. If my X is liters, moles over molarity equals liters. Typically, I'm not going to give you moles. That's for certain. But you know how to go back and forth. Or, if I ask you to solve for moles, by multiplying by the molar mass, you can get it back to grams. There are 3 practice questions for you to do on Google Classroom in a Google form. Try it. See if you can solve for molarity, moles, or liters, or grams by plugging and chugging to get your values. We'll be back on Thursday to do another application of this. And then your final assignment for the year will be a quiz using molarity and dilution, which we'll learn about on Thursday. Have a great day. I will be in Google Meets today at 10 a.m. and at noon.